Good afternoon, everyone. I'm Kuchling. Thank you for coming to my talk today, which is on computer recreations. This is trying to rediscover some programming amusements from the 1980s that I think still have some relevance today for education and amusement. So where this starts is in the pages of Scientific American magazine. So Scientific American is a magazine with a long history dating back to 1845. And the graphic design of it has changed over the years. From the newspaper-like 1840s to this jaunty little 1922 painted cover to the clean white space of the 60s and 70s. It's still around today. And one of the big traditions for the magazine in the 20th century was recreational mathematics, thanks to this man. This is Martin Gardner, who is a columnist in Scientific American for 25 years, 296 columns from sometime in the 1950s to around 1981. And in his column, called Mathematical Games, he covered topics such as chess problems, topology, magic tricks, which he was fond of, things like game theory, and a lot of other math-related things. And all of Gardner's work has been collected into a series of books. And in fact, he's standing in front of them all. That bookcase is filled with all the varying editions and translations of everything he ever wrote. So Gardner started in the 50s, an era well before computers were very common. And so he didn't touch on computing topics very much. One exception, though, actually had a big impact. The October 1970 column was on John Horton Conway's Game of Life, which I think many people are familiar with. In the Game of Life, you have this array of cells that are alive or dead. Cells with exactly 3 neighbors come alive, and cells that are alive stay alive as long as they have 2 or 3 living neighbors. And so you have these patterns which evolve and change and propagate themselves. And it led to a little boom in the 70s of people using lots of their employers' computer time to run life patterns and work things out. And there was some interesting mathematics here. One interesting discovery is that life turns out to be computationally equivalent to a Turing machine. And in fact, someone has created a pattern that is in fact basically a universal Turing machine that takes a stream of input life patterns and acts on them. So Gardner started to step away from the column around 1980, and the magazine wanted to keep it going, so they hired a replacement. This is Douglas R. Hofstadter. He took the name Mathematical Games and anagrammed it and called his column Metamagical Themas. And he was well known at the time as an author of that book, Gödel, Escher, Bach, An Eternal Golden Braid, which won a Pulitzer Prize for nonfiction in its year. So Gödel, Escher, Bach discusses the mathematical logic of Kurt Gödel and the symmetric art of Moritz Escher and the musical patterns and variations of Johann Sebastian Bach. And these don't sound like these topics are related at all, but he ties it into self-reference and patterns and the nature of consciousness, even. It's an astonishing book that you will either hate or love. So Hofstadter, I think, perhaps was more used to the book form. He only stayed at the column for 2 years. And his columns were all collected in a book with the same title, Metamagical Themas. And it's worth checking out because there are some interesting things. There's one column in there where he discusses Lisp, presenting it as the language of artificial intelligence. So his replacement was this man, Alexander Dewdney, who is a professor of computer science at the University of Western Ontario. And he shifted the column yet again, changing its name to Computer Recreations. And its goal was to present recreational class problems that were well suited to computer investigation. And Dewdney's column ran throughout the 80s until 91, and most of his columns were also collected into a series of books. Now, this always feels to me like a really surprising thing, that a general interest magazine like Scientific American would introduce a column that spent a lot of time talking about basic and computer programming. So why did they do this at the time? So the 1970s saw the first introduction of computers that were small enough and cheap enough that an individual might reasonably own them. There were computer kits like this Altair or this Heathkit, but the interface wasn't terribly friendly. Notice the Heathkit has basically a hex keypad, and there are some LEDs, LEDs above the keypad, which are displaying the words CPU up. So this was really required you to be very dedicated, and often you had to assemble them yourself. But in the mid-70s, they began to be more accessible. There was a new generation of friendlier microcomputers, like the Apple II on the left or the Commodore 64 on the right. And they had actual keyboards with letters and everything. They connected to your TV, so you could actually display graphics. And often they supported sound as well that was basically compatible with, or at least at the same level as the video game consoles of the era. And there was a whole constellation of these microcomputers from various companies, most of which are now gone. Commodore's VIC-20 and 64, Radio Shack had their line, Atari had a computer line, Timex, Sinclair, Texas Instruments, and so on. So common features of these machines were that you would program them in some version of BASIC, usually provided by Microsoft. In fact, that was where Microsoft started, providing BASIC for the Altair. They generally had from like 2K to 64K of memory, and they supported pixel addressable graphics and sound. So you had these hobbyists who bought these machines and wanted to play with them. And so Computer Recreations was an attempt to appeal to this community of people. So what sorts of things did Computer Recreations discuss? I'll provide a brief glimpse of 3 examples that are still, I think, kind of interesting today. So the first one is a cellular automaton. I already talked about life when I was talking about Martin Gardner, but there are lots of similar models of cells on a grid that take on states and that change in some way. And so in one column, Dewdney discussed the cyclic cellular automaton. So you take a grid of cells with n states. In this case, n equals 6, so they go from 0 to 5. And for each cell, if it's in state n, if it has a neighbor, and usually the neighborhood was just like north, south, east, west, you didn't look at diagonals in this example, then the cell changes to state n plus 1. So for example, this pattern evolves like this. The 4 at the upper left is next to a 5, so it becomes a 5. The 5 itself is next to its successor, which is 0, because we're doing this modulo 6. And so on, and you end up where some cells change and some stay the same. So this is an interesting example you can give to someone to program in Python, or you can program it yourself if you're learning. I did a very simple representation of the board as a dictionary with the XY, with a tuple with the XY coordinate as the key. And so it's easy to fill in the board with random states like this. And then doing one processing loop consists of looping over the size of the board, applying the cell rule and building a new dictionary, and then we can update the board's state with that constructed dictionary. And finally, implementing the rule is the most complicated bit. And so we take a coordinate, figure out what its successor could be, and then scan the 4 neighbors. And we don't need to do anything special to worry about the edge of the board because we're using get on a dictionary. So if you access a coordinate that's bad, you'll just get back none, which is never going to be equal to the successor, and so it all works. So pre-recorded demo, let's see if I can hit play. So it starts out looking very random, just like snow. And over time, it starts to change. So you see it begins forming these sort of large areas of color, which Dewdney calls droplets. And so the droplets sort of grow and sort of collide. And then you start seeing these spiral patterns forming. And these spiral patterns then sort of grow over time and eventually take over the whole board. And it's kind of interesting behavior to emerge from a rule that really seems very simple. And you can then ask questions like why do certain coordinates form the root of these spirals or not? And the answer is, at every one of those spirals, there's a little loop of cells that are all sort of off by 1 from each other. And so they can change continuously. And they essentially serve as the nucleus of these spirals. So I think this is a nice example because you get pretty pictures and it's pretty simple to explain. And you can also play with it a lot by trying alternate rules. So the second example is a toy genetic algorithm. Dewdney called it the evolution of FLIBs, where FLIBs stood for finite living blob. So each little blob gets a string of bits as an input. And it's an organism, it's trying to predict that input and match it. So in this case, if this blob receives that input and produces that output, it gets a score of 62 because that's how many of them it got right. So looking inside, each blob is a little finite state machine, which is a concept that may be familiar from computer science courses in logic and computability. So the machine starts out in state A, and for each bit it receives, it outputs another bit, and also can transition to some other state. So it starts out in A, it gets a 0, it outputs a 1, and transitions to state B, and so on. So you can imagine handwriting, given an input pattern, handwrite the finite state automaton that would match it. It's kind of an interesting little paper and pencil exercise. But what we want to do here is we want to evolve it. So we can write this state machine out as a string representation. We write it out as a table, which sort of has the same content as the previous diagram, and convert that to a string just by reading left to right. And once we have that string representation, we can randomly generate a bunch of them, and then combine them, score them, and take the best ones. So for example, if we have 2 blobs with these particular genomes, we can combine them by picking 2 random indexes and then combining the 2 strings. And this is inspired by how DNA crosses over and how you get one stretch of it from your father and then another stretch of it from your mother and so on. And so you combine these and you get some new genome for a new blob that can be scored. And you can also mutate a single blob. Pick a random one, pick a position, and just pick a new value to store there. You can flip a 0 to a 1 or vice versa. Or if it's a letter, you can set it to sort of any one of the available states. We're assuming a fixed number of states for each machine here. So in the example here, and I won't present the code for that because it's sort of not very interesting. It's a lot of string manipulation and for loops. And you can wrap blobs up as an object of their own. So starting at generation 0 with randomly generated data using one particular random seed, these are the results I got. The worst score got 20% right, the best score got 75% right, and you can see the environment and the prediction. So after just 100 generations of taking the best and crossing it with some other randomly selected blob and putting that result back in the pool, we've improved things up to 90%. And the worst score has gone up a little, but the worst score bounces around a lot because we're often introducing a mutation. We're introducing a hopeful monster that turns out to not be very good at predicting. So it takes 1,500 generations to do the next 5%, where one blob finally managed to predict everything except one bit in 2 occurrences of the environment. So it predicts the first one perfectly, but it's left in some different state and it ends up getting it wrong. And finally, after 5,000 generations, you get a perfect predictor, and if you follow it through, you find out that it does in fact work. So genetic algorithms certainly can be done in a much fancier way. There's a package on the Python package index called genalg, which provides a sort of very powerful generic genetic algorithm mechanism. And it's actually not as esoteric a topic as you might think. If you use PostgreSQL as your database, that's probably the closest genetic algorithm to you. Because Postgres, when you join a lot of tables, and I think the threshold number is around 12 tables or so, normally Postgres tries to evaluate every possible execution plan and takes the optimal one. It scores them trying to evaluate how much I/O each plan will do, and takes the optimal one. But when you're doing that many tables, that's a lot of time to look at these. And so what Postgres will do is it'll generate a bunch of random query plans, cross them, run that for a fixed number of generations, and hopefully the same thing will happen as with the initial example, that you get this sort of big initial increase. And if it's only a few % away from optimal, that's probably fine. So my third example, I'm going to explain in a kind of elliptical way. I'm not going to explain where I'm heading, although some of you I think will come to recognize what I'm doing as it goes on. This was actually a famous one that brought a mathematical discovery to wide public attention. But I need to start by providing a 2 or 3 slide introduction to complex numbers. So first we'll define the magical number I, also sometimes called J by electrical engineers and Python programmers, that are the square root of -1. Now, if you remember your basic rules of arithmetic, when you multiply two positive numbers, you get a positive. And when you multiply two negative numbers, you also get a positive. And the only way to get a negative is to have two numbers with differing signs. So this seems like it doesn't make sense. I can't be positive or negative, but we can just, mathematicians being who they are, can just run with that and see what the consequences are. So we can express numbers as having a real part, which is just like an integer or a real number, and an imaginary part. And so the imaginary part is some number times I. And when you add two complex numbers or multiply them, it's just sort of fairly straightforward algebra of writing out the sums or products, and you get some new part. Another concept I want to mention is, so you can visualize complex numbers on a 2D graph, because they are just tuples or pairs of numbers. And so the distance from 0 to a particular complex number is called its magnitude. And Python happily supports them as a built-in type. And Python chose the J notation instead of the I. I think it was thought that I would probably be too confusing. And so you can write numbers down by appending a J, and that results in a complex number. There's also a constructor, and you can get the real and imaginary parts of the complex number. And you can also take its magnitude with the abs built-in function. Now, I want to pose a little question. Let's pick some random, arbitrary, fixed complex number C. And we'll start out at 0. And we'll square, well, we'll start out at our initial number Z. We'll square that number and add our constant C. And then we'll repeat that over and over, squaring and adding C, squaring and adding C. So what's going to happen to the values of Z as we go? Does it grow indefinitely? Does it converge? Or what? Well, so if you think about C equals 0, that's very trivial. It remains fixed, because 0 times 0 is 0, you add 0, and it remains the same. If you pick a number, a real number like 0.1, well, this, as you run through it, seems to be converging clearly to something. We can take a complex number, and here the numbers seem to be exploding. It starts out with the real part dropping in the second iteration, but then it grows to 3, and from there it goes down again, but the imaginary part has grown to 18, and by the 7th iteration, we're out in the 100,000. So this seems likely that it's just going to explode off to infinity. So let's pick a different complex number and see if the result is any different. Here, it's more confusing because the real and imaginary parts are just sort of jumping around in a very small range, kind of hanging around the origin, not really going anywhere. But they also aren't really apparently converging to anything. So it's straightforward to write a little Python function that tests this for some particular number c. So in this case, you pass in c and a maximum number of iterations, after which you'll give up. And we just loop through over and over, squaring our number z and adding c. And there's a theorem that if the point ever gets more than 2 units away from the origin, you know it's going to explode off to infinity. So at that point, when the magnitude grows that large, we'll just return the number of iteration steps it took. And if it didn't seem to explode off to infinity, we'll return 0. So if you plotted all the points that stay finite, what would that graph look like? So you might think, well, we're squaring stuff, so it's maybe some kind of circle of some particular size. Or you might think of algebra and parabolas and conic sections, and you might think it's something kind of swoopy, and that's like just a scribble. What you actually end up getting is a shape that you've probably seen. It looks like this, and is called the Mandelbrot set, or the M set. It's named after the mathematician Benoit Mandelbrot, who was the first person to publish and inquire into it very deeply. And it was A.K. Dewdney's 1985 column that really brought this to public attention. And it's a really fascinating thing because it's not a boring or a simple shape like a circle or a conic section. And so you see you have some circles, and you have the big kidney-shaped portion on the right, which mathematicians call a cardioid. But you also have all these smaller versions of itself branching off. And so if you zoom in, say, to one portion at the kind of in the middle on top, you see more copies of itself. And you can see some little fragments of dust up at the middle top of the image. And if you zoom in on those further, you see another complete copy. And you can basically zoom in forever. So it's this very complicated self-similar shape. And in fact, there's another theorem that proves that this set, the Mandelbrot set, is connected. So you can, from any 2 points within the set, you can walk from one point to the other while staying inside the set, which means that those little points up there are not actually islands. There's a little tiny thread of points in the set running out to them. There are a whole bunch of interesting mathematical things tied to this. I suggest you take a look at YouTube or search through Wikipedia for much more on fractals and the M set. So implementing it in Python is straightforward, but the result you get is kind of slow. Here I'm borrowing the numeric Python array type to represent the set, and this is just a straightforward set of nested for loops that steps through every x coordinate and every y coordinate and does the iteration. That works, it's easy to understand, it's not fast. Producing a 640 by 480 image takes about 10 seconds on my laptop, which isn't really that good. But in a recent weblog post, Jean-François Puget, and I linked to the post in the references, Jean-François Puget looks at different implementations of the Mandelbrot set in Python. And one he presents is this vectorized implementation with numeric Python, where you're acting across the whole grid at once. So, for example, so you fill in a grid with zeros, And then you create an array called C that sort of is every value of C, and then you map them in the for loop. And numeric Python has the feature you can use a Boolean array as an array index. And when you do that, every cell which has a value of true in that Boolean gets assigned a new value. And so that's what it's doing in the main loop. It figures out a not done array of Booleans and then assigns to only those that aren't done, and it keeps iterating. And this does the same image calculation in about a second. And I highly recommend looking up Jean-François' post, because he tries writing the simple thing in PyPy. He tries applying compilers like Numba and Python, and he even uses GPU packages to run it on his GPU, which ends up getting the time below a second. So to conclude, I think it's kind of unfortunate that this era has basically been forgotten today. Dewdney's column was collected into a bunch of books, which are all basically out of print today. And they're good for Python developers to use. They're more interesting than trivial or sort of made-up toy exercises. And Python today makes them much simpler exercises. Dewdney had to explain how to multiply vectors in BASIC, coding it index by index. But today the Python programmer can just use NumPy or Pygame or other packages to display stuff. So I looked on some used bookstore sites, and copies of these books are usually available for of the order of $5 US. Unfortunately, I've been unable to find any record that they were translated into Spanish. So I recommend the Armchair Universe. I think was the best one. It was the first collection and has a lot of really famous columns. The Magic Machine was a follow-up, and the Tinker Toy Computer was a third. There's actually one more book by Dewdney that's still in print and may still be worth checking out. The New Turing Omnibus was from 1993. It's 66 short chapters on computer science topics. Things like how you draw spline curves, logic and theorem proving, game trees, Turing completeness, NP completeness. Some bits of it have dated since 1993. Chapter number 53 is on disk operating systems, so it talks about the anatomy of MS-DOS a bit. But a lot of the topics in it are actually more evergreen than that. At about 10 pages per topic, it's not a lot of depth or rigor, but it's an enjoyable broad survey of computer science topics, and it could steer you to finding things you'd like to enjoy, you'd like to explore more. I also think there are probably more interesting things hiding in the magazines of the period that could be mined for pedagogical use. So, like this magazine, Creative Computing, usually ran program listings in every issue. And they had a spin-off series of books called Basic Computer Games. And it's interesting to browse through these and look at what people were doing, the retro ads and artwork, which can be amazing or horrifying. And a lot of these are available. There are sets of scanned copies of them on archive.org. My references are given in this presentation, so you can look the slides up on speaker deck to chase the references down. So at this point, I'll stop and I'll take any questions. And thank you very much. So any questions? Yes.
You have some kind of library or repo with these codes?
I do. I haven't actually published it because a lot of the code was written in a sort of rush and is kind of hacked together and experimental. But I probably will publish that at some point once I've cleaned things up. Yes?
Do you have any idea how hard or plausible it would be to write some sort of script for checking, for not for the graph you showed, but for like Julia sets, like to find interesting parameters for those?
That would be an interesting thing, actually, because you could,
You could
how
try
do you
like how
define
many
interest?
different values, right? Like they take for a number of iterations to get, right? And it's like, oh, you only took on 2, you probably won.
Mhm.
But it also seems like you'd have to search for a lot of values. So.
Yeah, you'd probably have to combine evaluating the Julia set with some measure of what you consider interesting. And another thing in drawing fractals is you can also mess with color schemes. How do you present the different colors and how far it takes to iterate. Piquet does that in another column where he applies sort of color bands and then smooths them. There's some other thought I had, but it's gone now. Maybe it'll come back. Thank you.
How do you feel these topics compare to some of like the code bomb and like other programming challenges, like even like weather and things like that?
So I'm not that familiar with code golf in specific. I think of code golf as like trying to get things in one line, which is an interesting sort of language syntax stunt, but it's not terribly interesting in that. Project Euler, I haven't done much with it. Project Euler, I think, seems very mathematical to me, so it does sort of intersect with this. But there are also things, he did columns on Markov chaining to generate text, and generating caricatures of a person's face by sort of having very simple, small outlines. At one point I sort of had the idea of trying to write something like an updated version that did more examples and did them in Python. And I just started, I started writing it, and you can find the relics of it at 50examples.readthedocs.org. But I eventually decided I'm not the person to write it first, and second, I wasn't really sure who my audience was. Is my audience people learning, or is it teachers who will take these examples and then sort of use them for students? And so I ended up sort of, in different sections, I sort of fall between these two chairs. Okay, all right, thank you very much for coming.